Hi! In this video, I'll be continuing the journey of cardinality. We went through when two sets are equinumerous. We've shown when a set is finite, when a set is infinite. We've found a criterion using the subset principle of infiniteness. And so the next idea is, are there sets that are infinite that is like countable? Can you count the set even though it's infinite? When are sets able to be counted? And so this idea gives us the concept of denumerability in the infinite case, where objects in a set can be listed out using the natural numbers. And so X is infinite and called denumerable if there exists a bijection with the natural numbers. You can also say it's enumerable, but these are just terminologies. And so with that idea, it also leads us to say when sets are countable, because denumerable is for the infinite case, and so you are countable if you are finite or denumerable. That's quite an intuitive definition to make. And then if you were to make the countability definition first, then you will say that X is denumerable if X is countable and infinite. And also this denumerability is also known as countably infinite. And so these are definitions that you can read through again and be familiarized with. And so the idea is that you want to list out a set. And so by listing, you are actually labeling it. And by labeling, you are actually just using the natural numbers. And so the idea is just to have a bijection with the natural numbers. Now, you are uncountable if you are just not countable, meaning you are not finite, meaning you are infinite, and you are not denumerable, means you do not have a bijection with the natural numbers. And so this leads us to our idea that we want to find a way to capture the idea of finiteness and denumerability in one sentence, in one theorem. And so instead of finding two things, proving two parts, you actually just need to prove that if there exists a surjective function from n, remember now n must be the domain, then A is countable. The converse holds as well. But let's talk about this theorem first. So if there exists a surjective function, meaning every element in A, there is an input from the natural numbers, and you can just label that by what natural numbers is its input. And so you realize that A can be listed out as it by the natural numbers. And so that means there is either denumerable or finite, because maybe A stops at n elements, then here could have more, but it's all listed out already. And so the converse holds as well, and that if A is countable, there will exist a surjective function from n to A. And so with this, you are able to prove when sets are countable, and instead of always finding a bijection, you reduced it to actually finding a surjective function. Now let's talk about certain properties of countability. Well, if A and B are countable, then A union B will also be countable. You can define the function as follows, and you just need to check that it's surjective. Well, because if Y is an element of A, then F is being countable, means there will exist an n such that Fn equals to Y, and then H just needs to equals to 2n, which will just equals to Fn, which then equals to Y. And if Y is not an element of A, it means that Y must be an element of B, because Y is an element of A union B. And so there will exist a n from in the natural number such as Gn is Y. Then you just need to take 2n minus 1, run it through the function H, which is just equals to G of n, then it's Y. And so H is surjective. And this proves that A union B is countable. You can then extend using induction to prove that a union of finite sets are all countable when each set is countable. But to prove it for the infinite case, where you want to prove that the union of countable union of countable sets is countable, requires the axiom of choice, and so I will not prove it. But just take the idea that when you have any countable sets that you run through, that you union all these countable sets again, then it will still remain countable. So the countable union of countable sets is countable. And then lastly, we can also prove informally here, but you can make this into a formal definite of function defined formally. But the idea is that you have a snake following, or diagonal if you will, like this. And this actually proves why A cross B is countably infinite or countable also. Because if they are both finite, then of course countable. And if A and B are countably infinite, then A cross B is also. And this means that if A and B are both countable, A cross B is countable. Hence, you can prove that n cross n is in bijection with n. And so, because n cross n is in bijection with q positive, which is in bijection with q negative, and you know the union of countable sets is countable, this means that q positive with the 0 plus q negative is countable, and because there is infinite, is denumerable. And hence, this represents q, and so being denumerable means it's in bijection with n. And then now you want to have criterion for when sets are countable instead of always proving using surjective functions. Because sometimes the surjective function is quite hard to form. So if you're able to say that A is denumerable and B is an infinite subset of A, then B is also denumerable. And it is the same idea as when we prove the idea for countability or the infinite criterion. And so the corollary of this is that if A is countable, this is countable, and B is a subset of A, then B will also be countable. And then if you just take the contrapositive, B is uncountable, will just mean A is uncountable. And the proof is of course similar to when we prove the criterion for infiniteness. And so I'll leave it to you to try it out for yourself. I've come to the end of this video. I hope you have enjoyed it. And a sneak peek of what is proven in the next parts that is a bit harder to understand is when you prove that R is actually infinite. I've left the proof for you to read, but the idea can be found in the textbook and it's written pretty well. So I'll leave it to you to read that part. Hope you have enjoyed it, and I've come to the end of the video. Thank you for listening, and feel free to like, share and subscribe, and leave any of your comments down below. Thank you.